Hey there. In this video, we'll look at the derivatives of the exponential and logarithmic functions. And I've listed those here. It's assumed by the time you watch this video that you know already that the derivative of the exponential function is, drum roll, the exponential function. Okay, one of the amazing facts about E. Okay, in some sense that's what makes E E. Okay, and then we have the exponential function base 5, or any other base other than E. And then we look at the inverse of the exponential function, which is the natural logarithm function, and the inverse of the exponential function base 5, which is the logarithm function base 5. Okay, so this video will focus in particular on how to calculate the derivative of the natural logarithm function. Okay, so let's dig into it. What is the formula for dy dx? Well, let's stop for a moment and think about what a natural logarithm is. So we begin with an input called x. We run that input through the natural logarithm function, and we then produce an output called y. Okay, if we were to run that process exactly in reverse, we'd be doing the inverse process, and of course the inverse of the natural logarithm function is the exponential function. So if we read this backwards, it says y is now the input to the exponential function, and we produce an output of x. So if I write that up, we get the following. Use y as an input to the exponential function, and you'll produce an output of x. Okay, let me just clean that up. So really, again, Formula 1 and Formula 2 are mathematically equivalent. They're just saying the same thing in different ways. And so you may wonder, well, what's the point? Well, the point is that we know the formula for the derivative of e to the x, and so, or e to the whatever. And so we can use that to our advantage in calculating the derivative of this inverse function. Okay? So for this next step, I'm going to, again, diagram things out. According to the first function, we're feeding x into the log function and producing output y. And according to the second formula, we're taking y as an input to the exponential function and producing output x. And so we can ask about rates of change. So when we go and hit this with the derivative, what is the derivative of, what's the rate of change of the exponential? What's the exponential? And what's the rate of change of the log function? Well, that's what we're trying to find out. So we'll just have to use the symbol dy dx. And the chain rule says if you want the derivative, you need to take the product of these two guys. So we're looking at the slope of the outside at the inside multiplied by the rate of change of the inside. And that's what the chain rule tells us to do. Okay, next we need the slope of x, which is just 1. And so let me just make some room here. Okay, next step, just divide. We'd like to isolate the symbol dy dx. And so we just simply divide by e to the y, and we get 1 over e to the y. And there is the derivative formula for the log function. Okay, and if you have a point on the log graph, you can go ahead and plug in x and y. In fact, we can just plug y in, and we'll get the slope. As usual, though, we'll go one step further with this and try to express things in terms of the input x. Okay, so in order to do that, we're going to use this relation right here, which tells us the code to change information about x into information about y and vice versa. And so we see that e to the y is just x. So we can take out this chunk, e to the y, and replace it with simply x. And so what we end up with is a formula for y prime. Y prime is given by the very simple formula 1 divided by x. And that is the derivative formula for the logarithm function. Y prime is 1 over x. Okay, let's look at two examples, or really one example from 2 points of view. A favorite technique of mathematicians is to look at the same problem from multiple perspectives. So what if we're trying to compute the derivative of this function, which is not quite so simple as log x? Well, we have two choices. We could just use implicit differentiation in the same way that we derive the formula for log x. We can use the same technique. Or we could use the rule. So let's do it both ways, and I'm actually going to clock it so that we can see how things go. The advantage of method one is that implicit differentiation is just fundamental to know to master the subject. You've got to know how to do that. So you might as well develop your speed and your skill. You're very unlikely in a pinch, if you find yourself needing to use that skill and you actually have mastered it, you're very unlikely to forget what to do. Okay, because this is conceptual knowledge. On the other hand, when it comes to rules, you may or may not remember it when it comes time. But what I'm going to do is just do a timer here so we can see what's involved in using this technique. So mark it, set, go. Let's go ahead and compute the derivative of this function. So I'll rewrite it in terms of e. I'll hit both sides with a derivative using the chain rule as I do so. I'll divide both sides by e to the y. And of course I can replace e to the y with the formula for e to the y, which is x cubed plus x. X cubed plus x. And I'm done. How long did that take? Just under, well, just about 45 seconds. Okay. So I was able to come up with a formula for the derivative using the technique of involving inverse expressions and implicit differentiation. Okay. And in doing so, I'm essentially repeating the steps involved in the proof of the more basic formula. And there's really something to be said for that. Did in under a minute. Okay, I understood exactly what I was doing at every step. I could do similar problems using that technique. Very useful. Okay, let's, however, go ahead and just to be fair, let's see what's involved in using the rule. So what does the rule say? The rule says if you have the logarithm of u, some function of x, and you want the derivative with respect to x, you've got to keep in mind that x has already gone through some process u, okay, and you would like to compute the derivative. So what you need to do at that point, okay, which then I left out, then goes through the logarithm function and produces, let's say, output z. So in that case, the chain rule would tell us you have to find the derivative of log y, or sorry, log blob, which is 1 over the blob. And so if our input was, let me relabel my symbols here. This is supposed to be called u. Okay, so you get 1 over that input. And then, of course, you have to multiply by the derivative of this. Okay, so this is the derivative of the log function. The derivative of u is simply what it is. You can only, if we don't know what u is, we have to use a symbol to represent it. So the rule would tell us, do you want the derivative of log of something? Then take 1 over that thing and then multiply by the derivative of that thing. Okay, so this is just a chain rule applied to the log function. Okay, so let's see what happens. Let me see if I can leave this up, but also give myself a little bit of room to operate. So here goes. I'm going to now reset the timer. In all fairness, we might as well see how long it takes me to use the rule. So here goes. Ready, set, go. And so I'm going to write y prime is 1 over the stuff times the derivative of the stuff. Okay, and that only took me just over 20 seconds. Okay, so I did it in like under half the time. And nothing wrong with that. In fact, probably a good idea to get used to doing that, but also good to have in your repertoire that you could just simply use. You could stick to implicit differentiation and get the job done in that way. And that technique will come up in a whole variety of other contexts involving exponentials and logarithms. Okay, so with that, by the way, can we just stop and check? Are these answers actually the same? Can I highlight that for you? Is this answer the same as this answer? Well, clearly they are. If you just apply your fraction rules, you're going to get this numerator and this denominator. And they are indeed the same. Okay, so with that, we've solved this mystery. In regards to the derivative of the natural log function, we produced the formula 1 over x. And in the upcoming video, we'll take a look at exponentials with a random base other than e, and logarithms with a random base other than e. Hope this was helpful. See you next time.